Okay, good. So let me share the contents. But before that, let me show you one example of a silicon wafer. Can you see this? Nampak tak? This is a. Can you see this? Can you see, right? Okay. So this is a this is a sample of solar cell. Uh, it's a it's a 6 inch in size. So it's about the width and the height here is about 15 something cm. So ini based on wafer yang dah difabricate solar cell lah. So last time I remember showing you pictures of monocrystalline and polycrystalline silicon wafers, and this is one example of polycrystalline. You probably can't see that clear in terms of the grain reflections, the different reflections of the grain. They look blues, uniformly blue. So or the blue color here on the silicon belongs to silicon nitride thin layer coating, or we call it ARC. If you remember anti-reflective coating that we learned last time from 386 when we did device presentation. So it's about 75 nanometer of silicon nitride. So it gives the silicon blue color because of the reflection in the short wavelength region between 300 to 500. This silicon wafer is originally gray in color before the solar cell fabrication. So all these lines, 1, 2, 3, 4. So these are called bus bar, empat bus bar ini to collect the current to the outer circuit. So you can't see clearly on the horizontal or the horizontal plane here. There are also tons of metal contacts running through horizontally, so it's not that clear because they are so small. And at the back, it looks like this. So gray color, gray and white scale, gray whitish. So yep. So you're gonna have this. You're gonna have this 60 to 70 of this in one solar panel. So for one solar panel, they so each normally contains of 60 cells or 72 cells, the common ones, right? So if you have 60, then it's 12 by 5. So if you have 72, then it's 12 by 6, right? So this one is silicon wafers, but used for solar cell fabrication. So the shape is square because we want to maximize the area for light collection, for current collection, because you want to absorb everywhere. So kalau kita pakai ni in round shape, then we're gonna waste spaces between wafers to wafers. On the other hand, for integrated circuit, we just use round wafers because equipments are heavy made that way. Yeah, but it's not gonna be optimized for solar cell. Okay. So let's get back to the slides. So you can see the slides now. Nampak? Yes, okay. So let's continue from here. All right, so yeah, have you found out this? What's the chemical used for soil damage removal process? What do you use for the damage removal process? Anyone? Can write KOH. Ada lagi? Any other solutions? KOH. What is KOH? Potassium hydroxide, nitric acid, HF. Lagi. Sodium hydroxide. Yep. Okay. So, okay, if you talk about monocrystalline, we normally use KOH or NaOH or TMAH. Satu yang tak sebut ialah TMAH ya, timah. Tetramethyl ammonium hydroxide, right? That's timah. Tetramethyl ammonium hydroxide. So you can use either one of these, KOH or NaOH or timah for damage removal. All right. How much do we have to remove? Berapa banyak silicon we have to remove from this process? So when you read about the chemicals, you must have read a little bit about how much needs to be removed. Any idea how much? Kalau you ada wafer thickness yang I don't know, maybe 500 micron. This one is yang for solar cell ni is very fragile. Saya kena pegang elok, kalau tidak dia akan pecah. It will just shatter macam pecah. So I'll need to handle it properly. And this one is like, this one is 180 micron. So ketebalan, if you look at the side here, if you look at this angle, so the punya thickness is like twice of our hair thickness, more or less. So assuming our hair thickness is 100 micron, so that's about twice. So how much do we need to remove? Kalau you ada 500 micron, then how much do you think we need to remove before we can actually do the process? It's normally 5 to 10 micron per side. So it's about 5 to 10 micron per side. It depends on, if you read, then you'll find that it depends on what of cutting process do you use to slice the into wafers. Sebab kalau you pakai different technology, different process untuk slice, then you will actually introduce different amount of damage to the surface of silicon wafers. So that will then determine how much do we need to remove for the wafers to be usable for device. Okay. So that's soil damage removal. Okay, wafer dimension and attributes. So the diameter can be, well, it can be 200 mm, 300, 400, 450. But the typical ones for wafer fab are 8-inch, 200 mm, or 12-inch, 300 mm. Quite a rare one is 18-inch, 450 mm. Okay, so the thickness ranges from 600, 700. Yeah, so that's a typical thickness of of the silicon wafers being used for IC fabrication. They need to be very thick, right, to handle the process and everything. On the other hand, we don't want this to be so thick in solar cell fabrication. As I told you before, solar cell fabrication is about technology cost. So you want the world to adopt the technology, the green technology, so it has to be cheap enough to be affordable for everyone. So then we have to drive the USD per watt to be as low as possible. And one way to do that is by reducing the amount of silicon that we use in the solar cell. So reducing amount of silicon means reducing the thickness of the silicon. So that's why thickness of 180 micron is currently being used in solar cell fabrication. So with this table, you can also see the area, the weight, and the weight in pounds as well, grams. Okay. Okay, wafer dimension and attributes. For the same chip size, if you look at this example, if you're running the same, if you're fabricating one chip with 1.5 times 1.5 microprocessors on 200 mm, you'll fit about 88 dies. Whereas if you go for a bigger wafer, 300 mm, so it's a shift from 8-inch to 12-inch. So you can fit roughly about triple, so 232 dies if you go for bigger wafers. But this 1.5 times 1.5 is considered big already. If you go for smaller technology node, then each chip size is perhaps a lot smaller than this. Okay, this is just an example for comparison. Right, these are other other parameters that we need to see in the silicon wafers. Diameter, thickness, warp. Right, this is warp. Warp ni dia punya apa? You don't want to have warp. Dia bengkok thickness variation, 9-point thickness variation is also called TTV. Total thickness variation, TTV. Hold on. You want the TTV to be minimum as possible. Depth, notch, angle. Notch is the home position yang saya explained a few days ago. So that's a notch. Notch, 0 angle, 0 degree, or home position we call it. Then the finishing of the surface, either it's polished or non-polished, single side or double side, like you asked in our previous class. Then the next process is called lapping. Lapping looks like when you run one process in the wafer fab, typically it runs in a batch, of many wafers. So kita tak run single wafer apa ni ataupun minimum number. We try to pack as many as possible as long as the process quality can still be delivered. So we try to push as many wafers as possible. And in fact, this is also tracked in wafer fab. If you talk about wafer fab, we normally label this as WPH or wafer per hour. So wafer per hour. Every machine dalam wafer fab dia ada dia own WPH. So if you have higher WPH, then you'll be able to produce more wafers in a week, in 2 weeks, in a month, in 1 quarter, in 6 monthly, in a year. So we normally, kalau you kerja as a process engineer later on, or in fact equipment engineer, so this will be among the what we call parameters that you work on, probably as one of your side projects. So when I was in lithography last time, WPH was one of my main projects as well. So we need to increase the WPH of the equipment or the process recipe in order to produce more wafers per hour with comparable quality or better quality. So it's normally very difficult because when you try to speed up the process, naturally you will it will compromise certain, certain properties or certain qualities of the process. But if you have to do that as one of your projects, then what you have to deliver is higher WPH with comparable yield or comparable quality in the device. So WPH. Slice wafers are mechanically lapped using counter rotating machines. So one is rotating clockwise and the other side is rotating counterclockwise. And we have aluminum oxide slurry to do the lapping process. So what it does is it will flatten the wafer surface because we have just finished with our damage removal process. So when we finish the damage removal process, the surface will be quite rough. It will not be so rough, but then it will be of some roughness that is not tolerable for the device. Kalau punya surface is very rough, then just imagine what's going to happen if you deposit a very thin layer of oxide later on. Kalau you buat MOSFET, then just imagine how ox would sit on your silicon if the surface is not smooth. So it has to be perfectly smooth. So this is one of the processes that ensure that the surface is in the best condition. So flattens the wafer surfaces, makes them parallel, reduces mechanical defects, saw markings, and everything from the previous process. The correct wafer thickness is also produced by a lapping process. So you can also tune the thickness because the moment you do the lap process, you are actually removing the what you call the non-uniform parts. So indirectly, you are actually reducing the thickness of the wafers. Okay. So this is how it looks like, the lapping machine by Mitsubishi. So you have wafers there. So after the lapping, wafers are etched again in a solution of nitric or acetic acid or sodium hydroxide to remove microscopic cracks, surface damage produced by lapping process. So even though it's supposed to remove the defect, it also introduces some defect as well. At a tolerable counts, I would say, because the process is mechanical in nature. So the moment it's mechanical in nature, it's actually touching the surface of the wafer to do the job. So the moment you have touching mechanism during the process, you might also hurt the surface as well. Okay. So acid solution is then removed by a series of high purity DI water. So after you've done with the etching process, the wafers are going to be rinsed a couple of times in order to make sure residues are completely removed. Then we'll go for polishing process. It's called CMP, chemical mechanical polishing. So if you look at, for example, if you look at Silterra has one department called CMP. Satu department ni. So the way it goes, if you want to know, the way it goes in wafer fab, at least for Silterra, I don't know how others are operating, but for Silterra, at least, every process is categorized as one department. So that means etch one department, thin film deposition is one department, CMP is one department, implantation is one, diffusion is one, oxidation, and so on and so forth. So in every single department, so we will have process engineers, we'll have equipment engineers, we have some process technicians and equipment technician as well. So those are typically looks like. In lithography last time, I think it was 20 plus engineers in total. Combining equipment and process engineers about 30 something for a second. Then process tech, equipment tech, maybe up to 50 altogether in one department, and managers and head of departments. So that's how it looks like. So after etching process, are polished in a process called CMP. So it involves chemical and mechanical polishing. So wafers are held in a hard ceramic chuck. So there'll be a chuck handling the wafers, and then a polishing slurry will be used. Slurry ni macam what you call, macam biji-biji lah yang kita pakai untuk do the cleaning in order to clean the. Dia punya effect dia macam sandpaper lah, if you like, sandpaper punya effect. Right, polishing is a slurry, so we call it slurry. Silica powder, the air water and sodium hydroxide. So what it does actually, it will do the polishing, macam kita polish. That's how it looks like. So there'll be pads on upper side and on lower side. Polishing CMP ni macam, kalau you nak imagine the simplest version of CMP, macam you basuh pinggan lah, basuh pinggan. Imagine the plate is wafer, and then the sponge basuh pinggan tu is the pad, and then sabun kan you pakai dekat bawah sponge tu ada, if you imagine the what you call the yellow and the orange, no, yellow and green, not orange, the typical one, yellow and green punya sponge kan. The green one is the harder part, harder morphology to do the the cleaning process. And you have the sabun as your slurry, if you like, right? So you do the cleaning to remove the dirt, to remove the residue of your food. So that's defects. Those are defects. So then you do the polishing, just like the polishing of silicon wafers in Wafer Fab. So we have upper polishing pad and lower polishing pad. Then it will sit on a wafer, and then slurry will go in between, will run in between to do the cleaning process. Okay. So the wafers can be polished on single side or on both sides. Both sides CMP leads to more expensive wafers, yeah, because you clean both sides, and the quality of both sides are guaranteed. So that's why they are more expensive in comparison to single side polishing. Okay. Is it okay so far? Can you guys follow? Is it okay? Good. Right, we have a few more slides to go. It's not going to be so long. So silicon wafer requirement. So this is, if you like, critical dimension ataupun gate width of CMOS. If you imagine it's a CMOS, then the critical dimension is the gate length or gate width. Macam kita tengok waktu Moore's law hari tu, right? So wafer diameter 200, then it evolves to 300, but some still running with 200 because it is simply more expensive to set up a new fab with 300 mm. Everything has to be larger, scale up to 300 mm process. So the flatness of silicon wafer, micro roughness. So if you look at micro roughness, ada siapa-siapa sini yang pernah guna AFM for your FYP last time? Pernah pakai AFM other than my students? My students saya tahu lah. Pernah pakai AFM? So if you look at the RMS, so it's done by AFM, by the way. So if you look at the micro roughness RMS, row number 3, nanometer in the unit. So look at the RMS roughness of the polished wafers. So the RMS is about 0.2, 0.15, 0.1, which is super duper smooth, right? It's very, very smooth. So this is produced by the lapping plus CMP. So we end up with 0.2 nanometer of surface roughness, RMS. Root means square. RMS means root means square. You can check it out. RMS means root means square. Root means square surface roughness, okay? Measured by AFM. Oxygen content, bulk micro defects, particle unit, epi layer thickness if there is an epi layer on top of the wafer. So another process is called gathering. Sounds like gathering, but it's gathering. It's a process of removing harmful impurities or defects from active regions of the silicon wafers where devices will be operating. So even though, if you look at this, defects from active area, okay, kalau you tengok dekat particles per unit area here in the last row, number of particles per unit area in cm squared, it's not that high though, but we still have to do gathering process, even though we have already made sure that the defects are already low from our growing process, from cutting process, from our lapping CMP processes. So still we have to do gathering process to uh, gather, if you like, gather to collect impurities from the active region of the silicon to one side so that they can be removed. So this is actually collecting the impurities to one side of the silicon, and then eventually they are removed. So how to do that? By providing an alternative location or a getter, we call it a getter. Basically, it's a place for us to collect all the impurities in the wafer. So where they prefer to reside, so they will come to that particular location. So it will be done by placing the wafer on high temperature treatment, somewhere 1000 degrees C, in nitrogen ambient. So what's going to happen is oxygen will evaporate from the surface. So if you have a high amount of oxygen to begin with, so some of them will actually evaporate from the surface, then leaving lower oxygen content near the surface. Then it will also create a defect-free zone suitable for device fabrication. So, so I'll show you a short animation now. So additional thermal cycles can promote formation of oxygen precipitates in the wafer, can be used for impurities gathering. So thermal cycles here means if you run the fabrication process, so it will take like two months at least. So there'll be a series of high temperature processes through the 2 months. So this is called thermal cycle. So kalau the more you have, the more high temperature processes you have, so that means the thermal cycle will be more. Okay. So let us okay, after let me finish this and I'll show you gathering process. A cross section of defect-free near region of silicon wafer. Lower part shows silicon dioxide precipitates used for impurity gathering. So, so this is SiO2 precipitates. It can also be used to gather impurities or to collect impurities, and then they can be removed. So if you look at the top part of the cross section, you can't see anything. So it's a lot clearer up there. So that means the impurities are already removed from the top area because kalau tengok dekat apa ni kita punya CMOS, if you draw a cross section of CMOS, so this silicon, then you're gonna have source drain, then you also have your gate oxide, then you have your gate up here. So if you look at this, all these structures, kita fabricate semua structure ni on the top surface. So semua ni akan berlaku dekat atas ni kat atas ni. So your oxide will be somewhere there, oxygen source drain, and there'll be gate ox, and there'll be gate on top. So the top part of the silicon, if you like, will be used for the fabrication process. So this is called active area. Active area. Active region pun boleh lah. Active area. Okay. So the lower side, on the other hand, is not the active area. So you can use this area to collect the impurities, and then they can be removed later on. So now let me show you how gathering works. So let me share the page. Where's the page already? Hold on. PV manufacturing. White burner from. Hold on. PV manufacturing. Share. Okay, here. Okay. All right, can you see the page now? The gathering page? Boleh, okay, good. So this is from pvmanufacturing.org. This one is a website for teaching purpose by UNSW in Sydney for undergraduate program. So if you go to this page, I'll give you the link on eLearn. If you go down here, you can see a short video on the gathering process with some narration, but you can't hear it now. I'll just play it anyway. So it takes about 21 seconds to show the process. So you can see from here, this is done through when you run a diffusion process during the fabrication. Fabricate a thin layer of emitter of N type. So the wafer is P type, and then you create a thin layer of emitter on the front surface. So in this case, the front surface too is flipped 90 degrees. So the red one is actually the front surface. Red one you can see later on. So the green one is the silicon wafer, and then you will see how impurities move during the high temperature diffusion process. Okay, so those are impurities. So they will actually diffuse during the process. So emitter is formed. So impurities are migrating during the high temperature process into the phosphorus dope layer. So into phosphorus dope layer. So let me just replay. So when they migrate into the dope layer, so they will actually be accumulated in the dope layer. And then we will see later on, after we do the diffusion process, we'll form phosphosilicate glass or PSG. Then we'll remove the PSG by dipping the wafer into HF solution to remove. Then the whole impurity will be gone with the PSG layer. Okay, so this is how gathering looks like in a brief animation. You can see later on. All right, let's go back to the slides. Almost done. You can see the slides, right? Nampak slide? Okay, good. So gathering in IC manufacturing, primary unwanted impurities are metals. So we might have metals in our silicon wafers during fabrication, or in fact before fabrication, or during ingot growth process. So which increase recombination. So the moment you have metals, so we have learned about undesired impurities in 386 last time. So the moment you have shallow defects or deep level defects like iron, copper, and other metals, so they will actually increase recombination. There will be trap states in the band gap. So they will segregate to interfaces, resulting in interface states or electronic state, if you like. They will also precipitate and inducing a new conductive path. So when you fabricate your transistor, you want your conductive path to be your channel, just your channel. You don't want the carriers to flow through some other routes. So you don't want to have these routes, and these routes can actually be induced by having precipitation of metals in desired way. So that means kalau ada metal, dia akan form a route in which your carriers will actually be drawn to that new route and escape from the actual channel, right? You don't want that to happen. Desirable to remove metals to outside active device regions, backside or in the bulk, just like what I've showed just now. So we want to uh, get all the impurities to one side, usually to the non-active area, so that we can eventually remove them in a wet chemical process, and they'll be out of the silicon completely. Sources of unwanted impurities, it can be from the melts during the growing process, particularly if you talk about Czochralski process, so they'll be in the melt. So from chemicals, cleaning, etching solution, photoresist, in fact, that means along the fabrication processes. Handling, it can be from wafer tracks, it can be from tweezers while handling the wafers, it can be from the boxes or from the pot. that we use to handle the wafers, because they are all stored in the pot, 25 wafers each. It may also come from particles, and these particles may contain metal as well. Process chambers made of stainless steel, quartz. So that means, yeah, it can be virtually from anywhere in the fabrication process. Okay, so those are the sources of metals, metal contaminants in the silicon. So you can do a gathering process in a couple of ways. So this one can also be done. Argon is used to amorphize the backside of silicon. A wafer is heated to high temperature, in this case 550, regrows silicon. So this is another way to do it, right? But the common one is the one I've showed you now during the fusion process. So this actually depends on uh, where do you have the impurities, or the impurities that you need to remove. So if you have the impurities after the diffusion process, that means the phosphorus gathering during the diffusion is not so efficient. So you need to then revisit gathering efficiency during the after the phosphorus diffusion process. Yep, yeah, that's all. Okay, that's all for today. Do you have any questions? So we've finished with wafer preparation and gathering. Our next will be wafer characterization tomorrow. Okay, any questions? No, so far. Okay. All right, then. So I'll give you the link on Elan later on. Then I'll also upload the notes for tomorrow on Elan. Okay. So I'll see you again tomorrow, inshallah. Bye bye. Assalamualaikum.